4.1 probability distributions. So we're going to take a look at a couple definitions first. The random variable X. So the capital X describes in general the desired outcome and has a single value, X, denoted for each individual outcome of an experiment. An example of this, going back to something that's familiar, the number rolled with a die. Okay, so if the random variable X is the number rolled with a die, X can be 1, 2, 3, 4, 5, or 6. Okay, and then we're going to take a look at discrete versus continuous. So discrete variables, a variable that can only have certain values within a range. So usually integer values, but not always. Okay. Example, points scored in a basketball game. Obviously, you can't have 2.5 points, right? So they're going to be integer values. However, money in Canada and United States does have 2 decimals, and those are still discrete values. Okay, and a continuous variable is a variable that can have an infinite number of possible values in a given range. Okay, these are often measurements. So height, time, blood pressure. Okay, although we round these numbers, like you go to a blood pressure machine at the drugstore, or you say, oh, I'm 175 centimeters tall. Although we round these numbers, they actually cannot be specifically or like exactly measured because of the complexity of that. Okay, so example 1. Let's take a look at random variables. We're going to classify each of the following as discrete. We'll use a D, or continuous. We'll use a C. Okay, the number of phone calls Sally's mom makes at Christmas. Well, that's discrete. You can't make half a phone call. It's going to be integer values only. The length of time Sally's mom spends on the phone. That's continuous because we're taking a look at the length. Okay, number of and then length. So that's a measurement. Okay, we usually use hours, minutes, seconds for time, but down to like the millisecond and so on, we can't actually conceptualize or maybe measure. Okay, a company's annual sales. Sales is money. Money goes to 2 decimals. This is discrete. Okay, number of cars sold by Honda. This is discrete. You can't sell half a car. Okay, and then distance is a measurement, so that's going to be continuous. Okay, the distance from your house to your school. Okay, now let's take a look at what a probability distribution is. So it's a table, formula, or graph that provides probabilities of a discrete random variable, and it outlines all of the possible outcomes. Okay, so that is the main focus here. In other words, like if you actually take a look at the word probability distribution, it's how all of the probabilities are distributed amongst the outcomes. Okay, so every single probability has to be between 0 and 1, and the sum of all the probabilities has to be 1. Okay, and then what we're going to do is we're going to graph these probability distributions in a histogram. Okay, so a histogram is used either with continuous data, okay, because what happens is a histogram has touching bars. So it's just a bar graph except for the bars touch. And because we use it with continuous data, it shows by the bars touching that the numbers and those intervals are continuous, and it continues along like across a range of numbers. Okay. The other way we do this is when we regroup discrete data in intervals. Okay. This is the only time we use histograms. Other than that, we'll use a bar graph. Okay. Technically, when you get up in like further years, we're gonna see that a graph of the probability distribution in which equal intervals are marked on the horizontal axis, like that's normal, and the probabilities associated with that interval are the areas of the bars. Okay, we're not going to focus on this too much in this course, but that is what you will see in university. Okay, so essentially, if the width of the bars here is 1, then the probability here, say 0.25, it's going to go up to here. But if the width of the bars is 2, this bar would actually only go up to 0.125. Okay, that's what that means. All right, let's consider the experiment where two six-sided dice are rolled and the sum of the up faces is noted. Suppose one die is red and the other is blue. One being red and the other being blue just is used to show like die 1, die 2 type of idea, okay? So we're going to identify the random variable here, okay? So let x be the random variable of the sum of two dice, okay? And we'll go ahead and we'll fill in the table. And then we're going to transfer the table into the probability distribution table, and then we're going to graph it. Okay? So, red die, blue die. Okay, if we roll a 1, 1, we get the sum of 2. 2, 1, 3. 3, 1, 4. Okay, 5, 6, 7. You're going to notice a pattern because each one of these numbers here and each one of these numbers here increases by 1 each time. I'll clean that up. So we can just increase by 1 each time. So 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8. Or you can say 3 plus 2 is 5. 3 plus 3 is 6. 3 plus 4 is 7. Okay? But knowing that each of these increases by 1 really helps the pace. I was looking at 6 and 6. 6, 7, 8, 9, 10, 11, 12, 8, 8, 7. Okay? So, transferring this to the theoretical probability, we can only get a 2 one way. So this is 1 out of 36. And we know that this is 36 because there is 6 options for each. So 6 times 6, we essentially have 36 boxes there that we had filled in. Okay, we have 2 3s. We have 3 4s. Okay, we have 4, 5, and 6 7s. Okay, 7 is the number that has the most frequency there. And after 7, it goes back down. So then it goes 5, 4, 3, 2, 1. And there's only 1 12 in our chart. Okay, so putting all of these frequencies over the total 36 is going to give us the probabilities. And if we add them all up, we get 36 over 36, which is equal to 1. So when we go ahead and graph this, I'm going to graph this as a bar graph instead of a histogram because this is discrete data. So they're not going to touch. Okay, so the sum of 2, if you think about it, it's going to have the same probability as the sum of 12. So I'm going to graph them both at the same time. So this is 0.0, almost 3. Okay, so for 2, 0.03. And then for 12, 0.03. Okay, and then we get 0.30, 2 divided by 36, 0.056, so maybe 0.06, just round up. Okay, and with that symmetry that we're seeing in here, right, between 3 and 11, I'm going to graph it for that one as well. So I get 0.083. So 0.08. There we go. Okay, 4 divided by 36, I get 0.011. No, 111. So I'm going to go up to like almost 11. 0.11. Okay, 5 over 36, I get 0.1, almost 4. So I'm going to go up to 14. Okay, and then up to 14 here. And then for that middle one, we're going to go 6 divided by 36, and I get 0.17, about 17%. Okay, so here is my bar graph. Okay, number 3, consider the task of selecting a random date in the month of September for a party. So just note that September has 30 days. Okay, so the random probability of selecting any one of those 30 is going to be 1 out of 30. Okay, but because it's 30 and I don't want to draw 30 bars on a graph, we are going to group this into intervals. Okay, so let the random variable x represent the date the party will land on. Okay, date as in like the number date. Okay, so we're going to fill in the table to outline the frequency and the probability distribution for the possible date of the party. Then we're going to calculate those sums. Then we're going to go ahead and create a frequency, a histogram, and a probability histogram using intervals. Okay, so frequency histogram, probability histogram, a little bit different. And then we're going to kind of draw conclusions when we compare those graphs. Okay, so as a recap, if we're doing the interval 1 to 6, a square bracket includes the number and a round bracket excludes the number. So that 6 is going to be pushed up to the next interval. Okay, so from 1 to 6, 1, 2, 3, 4, 5, there are 5 days there, making that a probability of 5 out of 30. Okay, 6 to 11, there are 5 days, so that's 5 out of 30. 11 to 16, 16 to 21, 21 to 26, 26 to 31. Okay, all frequency 5. So all of the probabilities are 5 out of 30. Okay, so 5, 10, 15, 20, 25, 30. The total frequency is 30, and the total theoretical probability is 30 over 30, which equals 1. So those both check out. Okay, now let's take a look at how to do the frequency histogram. So frequency, all of these pop up like the intervals, basically like from 1 to 6, that's going to pop up 5 times. Actually, I'm going to do it to 5. And the reason why is because then at 6, do it to 6. Yeah. And then at 6, we're going to switch over. So 1 to 5 is a frequency of 5. 6 to 11 has a frequency of 5. 11 to 16 has a frequency of 5. And I'm just shading these in. 16 to 21, frequency 5. 21 to 26, frequency 5. And then 26 to 31, frequency 5. Okay, so if we take a look at this, we do this one together because when we put discrete values into intervals, it kind of becomes continuous. Not the values themselves, but the way we graph it. So we can see that this is uniform. All of these frequencies are 5. And now what we're going to do is we're going to do the probability histogram. Okay, so if we have 5 divided by 30, that's 0.17. So 0.17, well, I'll do the same colors here, okay? 0.17 here, 0.17 here, 0.17 here, 0.17 here, and we keep going. Here we go. Okay, 0.17. You can color these in, you can leave them, that's fine. Okay, now let's actually compare them. Okay, so I'm going to go ahead, color these in. Okay, so if you're taking a look, you might think for a second that these are the exact same graph. You really have to look at how it's labeled. Here we go. I'm not going to finish this. There we go. Okay, so let's take a look how this is labeled. We're doing frequency versus P at X. However, because the frequencies are the same, that probability is also going to be uniform. Okay, so the probabilities and the frequencies are both uniform in this case. We can see that with these two columns here. State any observations. So let's go ahead and state those. I'll state them up here. Okay. So they're uniform across. They look the same. Okay, they're the same intervals. And then there's just different y-axes. Because the same intervals on the x-axis. Okay, now expected value. Expected value represents the theoretical average or the mean value that would be obtained from a random variable over, and we've seen this before, a large number of trials or observations, okay? So this is as n approaches infinity. So as we repeat and repeat and repeat all the trials, okay, it's the long-term outcome. And just to remember, this is not probability. This is like the points or the dollar amount, okay? So there's like an assigned value. So we want to focus on the assigned value, do not just compare probabilities. Look at probabilities. And we've seen this before. Oh, I want to point this out. Here's a note. The mean value, or the mean is an average value and does not need to be in the sample space. Okay, so what we're going to do is we're going to add up all the XPXs. Okay, let's take a look. Example 4. Okay, a coin is flipped 3 times. The tree diagram on the right shows all possible outcomes. So we're going to determine the expected number of heads. Okay, so this one is 3 heads. This one is 2 heads. This one is 2 heads, 1 head. This one is 2 heads, 1 head, 1 head, 0 head. Okay, that's what I get. So 0 head, that occurs 1 time. So the probability is 1 out of 8. 1 head occurs 3 times. So the probability is 3 out of 8. Okay, 2 occurs 3 times and 3 occurs 1 time. Okay, so all of these probabilities, by the way, add to 8 out of 8, which is 1. Okay, so for expected value, we want to multiply the x times the p at x. So this is what we're multiplying here. Okay, so we get 0, we get 3 out of 8, 2 times 3 is 6 out of 8, 3 times 1 is 3 out of 8. So 3 plus 6 plus 3. We get 12 out of 8. Okay, this is under the expected value here. That's where we want to, we'll delete that. That's where we want to write in the sum, okay? So 12 over 8, the expected value is 1.5. So every time you flip a coin 3 times, you're expected to get 1.5 heads, okay? Note, you cannot actually get 1.5 heads. Okay, so that 1.5 is not in the sample space. The sample space here is the 0, 1, 2, 3. Those are all of the possible outcomes. Okay, 1.5 is not one of those, but that's okay. All the 1.5 means is that you're going to flip 1 and then you're going to flip 2. And that's going to be your average, the 1.5. Okay. Now, we can have the exact same game, but this time, for B, we will assign, you get $3 for each head tossed. So now the number of heads is 0, but your payout is 0. The number of heads is 1, your payout is 3. The number of heads is 2, your payout is 6. The number of heads is 3, your payout is 9. Okay, so now what we've done is we've taken the exact same game, but we've allotted a dollar amount to each outcome. So these probabilities are the same because it's the exact same tree diagram. Okay, and now instead of multiplying the number of heads by P at X, we're going to multiply the payout by P at X. So now we're multiplying these numbers. Okay, so I get 0, 9 out of 8, 18 out of 8. 9 times 1 is 9 out of 8. So I get 36 out of 8, which gives us 450. Okay, so now if this was the game, the expected value is 450. But what that actually means is every single time you play, right, as n approaches infinity, as you play more and more and more, you're expected to take home $4.50 every time you play. Okay, now we're going to do the same thing, but with the expectation for a discrete probability using frequencies. So this is now when the frequencies are not just 0. Do that in blue. Okay, so what we would essentially do is we would multiply the frequency by the XPX, the frequency by the XPX, and then add those instead of just XPX. Okay, so a summer camp has 7 4.6 meter canoes, 10 5-meter canoes, and 4 5.2 meter canoes, and 4 6.1 meter canoes. Canoes are assigned randomly for campers going on a canoe trip. So, show the probability distribution for the length of an assigned canoe. And then we're going to calculate the expected length, and then we can kind of interpret that, okay? So, X is the actual payout. So, our payout in this case is going to be the length of the canoe. So, we have 4.6, we have 5.0, we have 5.2, and we have 6.1. Now, essentially, if you think about 7 plus 10 plus 4 canoes, okay? We have 25 canoes. So the probability of choosing any one canoe is 1 out of 25. But the thing is, we're going to skip the part where we multiply that. What we're going to do is we're going to say, okay, how many 4.6 meter canoes are there? Well, there's 7 out of 25. Okay, and then there's going to be 10 out of 25. And this one's 4 out of 25 and 4 out of 25. Okay, and if we think about this probability, it is 25 out of 25, which equals 1. And now what we're going to do is we are going to multiply this. So we get 4.6 times 7 over 25. I get 1.288. Okay, 5 times 10 over 25, I get 2. 5.2 times 4 over 25, I get 0.832. And 6.1 times 4 over 25, I get 0.976. Okay, when I add these up, I get 5.096. So therefore, a randomly assigned canoe is expected to be 5.096 meters long. Nearest tenth, 5.1 meters long. Okay, if you think about like a weighted mean, this makes sense. So we're heavily weighted toward these numbers. And only a couple are, like 8 of them are higher, but 17 are weighted like 4.6 and 5. So if you're thinking about a weighted mean and where that middle ground would fall, it would be 5.1. Okay, last question. A lottery has $1 million first prize, so that's the payout. Let's write $1 million. Okay, $25,000 second prize, and $1,000 third prize. Okay, well, why are there 4 boxes here? Well, all the other people win $0. Okay, 2 million tickets are sold. So is one first prize, it has 1. Means 1. Okay, and it has 5 of these ones. Here's the thing. If they sold 2 million tickets and 7 of them had prizes, that means 1,999,993 have no prizes. Okay, but the frequency is going to add up to that 2 million. Okay, probability of winning this prize here, okay, the $1 million, is going to be 1 ticket out of 2 million tickets sold. Probability of winning 25,000 is 1 ticket out of 2 million sold. Probability of winning 1,000 is 5 tickets out of the 2 million sold. And the probability of winning $0 is 1,999,993 out of 2 million tickets sold. If you actually add up the probabilities here, they do add to 1. Now we're going to multiply the dollar amount, the payout, by the probability. Okay, remember this frequency was already taken into account here, so we don't have to multiply by the frequency again. Okay, leave the denominator though, because when we get down to the expected value, having a denominator that's all 2 million is going to be really easy to work with. Okay, so 25 times 1 is going to be the 25. Okay, 1,000 times 5 is going to be 5,000 over 2 million. And this is just going to be 0. So that's going to work out to 1,030,000. Double checking, yeah. Okay, if you want to actually divide that, we get 0.515. So let's round. The payout would be 52 cents. Okay, so the expected value is going to be $0.52. So each time, each ticket is worth 52 cents. Now let's take a look up here, okay? We created a probability distribution for the amount of money won. Okay, we calculated the expected earnings. So here's the difference though, okay? So everybody's expected to win 52 cents, okay? That's not an actual thing. Everybody doesn't win 52 cents. A few people win massive prizes. Everybody else wins nothing. But usually what ends up happening is, I'll do this in blue, the ticket costs $2. So if I'm expected to win 52 cents, but I spent $2 on this ticket, okay, what is actually the value of each ticket? So the actual value is negative 1.48. Okay, let's interpret this. Therefore, after paying $2 for the ticket, the value of the ticket is, let's go, a loss of $1.48. So this word loss accounts for that negative that would have been there.